and just identifying functions in general. And so, yeah, that's all I want to say there. At the end of this practice, so we're not going to spend the entire day on it. At the end of this practice, we're going to do a demonstrated understanding that has 6 questions, and then hopefully we'll get to the gold rush task on quadratics at the end. So all about linear versus exponential, but we still got to add in that quadratics at some point, if not today, but definitely be tomorrow. And this is actually going to be really important for Friday. We're doing a fun activity where I have a friend of mine from UWA is going to come in. He's going to bring in some physical activities to help us see linear, exponential, and quadratic really well and understand their importance in the real world. So we need to make sure we get through that quadratic. Right, Bella? I get it. I'm tired too. But come on. Y'all got this. Miles, do you have a name card, by the way?
I think so.
Okay. Remember, we got Mr. Javi trying to learn names, so please make sure you have those name cards out. All right. As a quick reminder, proficiency scales, I want y'all to look at it. I want you to think through and reflect on, can you for sure do this thing? If you can, mark it off. And so we're going to do an analysis. Up to this point, have we looked at determining if a relation is a function? Is that a skill that we have at least talked about, practice? Yes. So I need you to think about if you can do that thing. Have we identified the type of mathematical representation for a given relation? Okay, so think about, can you actually do it? If you can, check it off, right? Vocabulary terms within that, can you confidently use the word relation, function, and mathematical representations consistently with the right understanding? If so, mark it off. If not, those are things that you need to do some check your understanding problems on and stuff like that, because it's in the Frere models. And I maybe ask a question to start class. Given any mathematical representation, we got a paper there? Okay, I'll get some more for tomorrow. Given any mathematical representation, I can determine if a relation is linear, exponential, quadratic, or none of these. Have we done all of that? Which one have we not done, Elizabeth? Okay, we haven't really talked about quadratics yet. Hopefully, we remember quadratics a little bit from last year. We're going to go deeper into them, make sure we really understand them, hopefully at the end of today. So if you can't mark that off, that makes sense. It's okay. Determining if two relations or functions are equivalent and explain why they are equivalent. Now this is one I really want to hit on. I want to remind you. What does it mean for things to be equivalent? Be careful. It's not quite the same as equal. Because I can say 3x minus 7 is equal to 5, but that's not necessarily equivalent, right? Now, if I were to tell you 3x is equal to 12, these equations are equivalent. Why? Say again. So that would explain algebraically how to get that they're equivalent, but remember there's a phrase I keep using. They look different, but what? But they're telling the same story, right? So when we say equivalent, they may look different, but they are telling the same story. And you're right, if I add 7 on both sides, right, that creates the 0, and that shows me getting to that 3x equals 12. But why are they equivalent? Because they look different and tell the same story. I don't have to physically show the plus 7. I know they're equivalent though. In the same way, x equals 4. That looks very different from what I started with. But is it telling a different story than what I started with? The story's the same. If I substitute 4 in for here, it makes the equation true. 4 makes this equation true. It may look different, but it tells the same story. In the same way, and this is important for functions, I need us to pay attention to this. First off, anyone know how I got that point, 0, negative 7? You guys, we gotta know this one.
You got negative 7 because that's your y-intercept.
That's the y-intercept, right? But it's not just because that's the y-intercept, right? It's my y-intercept right here. But literally, if I substitute 0 in, what's 3 halves times 0? 0. 0 minus 7? Negative 7. What's another x value that I can substitute in? Another input. 1, I could do 1. I'll go ahead and tell you, I personally don't want to use 1, but I could. Because I would get 3 halves times 1 minus 7, that gives me 3 halves minus 7, which we could use a calculator for that. Can someone type in 3 halves minus 7 really quickly? Okay. What do you get when you type it into the calculator? Negative 11. Say that one more time. Say that one more time.
Negative 11 divided by 2.
Negative 11 divided by 2, because over is just a positional thing. But if I take negative 11 and I divide it by 2, what do I get again? Negative 5.5, right? Fractions, I will say, are way better to work with long term, especially when multiplying and dividing. So I will always write it as a fraction. But notice how we get a fraction out of that? What if I were to have used a 2, though? Why would I use a 2?
It would be a whole number.
It would.
A fraction.
Ooh, would it be a whole number? What do we mean by the word whole number in math?
A regular number.
All numbers, depending on your perspective, are regular numbers. Mr. Hobby, where did the whole number start?
Start at 0,
And then?
1, 2, and so on.
That's a whole number. Notice how this is negative. Does a negative fit within the whole numbers right there? Does anyone remember the term when it's the negatives like that? The whole numbers or their opposites? Say it louder. Integers, right? So be careful with our language. We need to be clear with that. Because if I say whole numbers, and this is the thing, I know some of you are like, but Mr. Kennedy, like, that's what I mean when I say whole numbers. But if I say whole numbers, I only mean these numbers. So we need to be clear on it. Because that's different than the whole numbers and their opposites, which is the set of integers. Okay? Now, does anyone know why I picked 2? Do you know how I knew that it was going to give me an integer? Not sure? Hey, Miles, can you read this for me real quick? Divided by 2. So what am I doing right here? Dividing by 2. So if I multiply by 2, I get 3 minus 7, and I get negative 4. You know what the next x value I might use is? 4. Because I noticed that what am I doing with this fraction bar? I am dividing. So, Mr. Kenny, I could just say over, you could, but if you recognize that as division, it's going to help you be intentional about your inputs. Also notice, why am I pointing out plus 3 and plus 2? That's the rate of change. That's the change in y divided by the change in x. So when I'm intentional about the numbers that I choose, it makes my life easier. And I could graph right from that equation, or I could get my table and graph from those points. But what I want you to remember is it doesn't matter which representation I look at, the same inputs map to the same outputs, right? Looks different. Does this table look like that equation? Guys, they're completely different representations. So do they look the same? No. But are they telling a different story? Different story. No. They're telling the same story, right? Make sure you, I know you're used to me saying, do they tell the same story? And that's why you're saying yes, but listen to what I said. Do they tell a different story? No. They are telling the same exact story. So, the idea of equivalence, hopefully that helps us later. Linear, we talked about. Exponential, we talked about. Equivalent, we talked about. Quadratic, not quite there. So, mark off where you are. Do note, if you have everything in the foundation marked off, which we could have everything in the foundation marked off, and we have some of the target marked off, what is your score on September 4th? What is your proficiency score? If you have everything in foundation and target marked off. 3.5?
3.0.
If you have everything in foundation and sum of target, 2.5. Right? See how 2.5 says I can do all of foundation and sum of target. If you can only do some of that foundation, only some of the target, what score are you at? If you can only do some of foundation and some of target, huh? Sum of foundation and sum of target. 1.5. Notice, so be careful. 2.5 very clearly says I can do all, right? 2.5 says I can do all of foundation and some of target. But if you can only do some of the foundational and some of the target without help, you're at a 1.5. If you need help, you're at a 0.5 or a 1. So think about where you are, because the reflection on where you are is going to help you know where to study. That's why you need to think through what can you actively mark off for yourself. And we're going to get practice with this today as well. Then I gave you the functions with constant rates of change. I think it's on the back side, or it's a separate sheet for y'all. It's one of those two. So is it a separate one? Y'all have it as a separate one. Okay. What type of functions have constant rates of change? I heard linear. Is there any other? And exponential, right? Remember, linear has a constant additive. Exponential has a constant multiplicative, right? Look, not Elizabeth. Mary, help me out. Do you remember what the name of the constant additive rate of change is?
I think I'm not sure.
Okay, so we want to know this off the top of our heads, and so look for it if you can find it. While she's looking for it, can someone tell me the name for the constant multiplicative rate of change? You don't have the constant rates of change one? Okay, let me look for it. Maybe. There's that. Okay, so that probably means, Bella, do you have the constant rates of change one? So that's just identifying, that's the constant rates of change one. All right.
Is it repeated?
So, well, constant additive rate of change is repeated addition, right? But there's a name for that constant additive rate of change. Well, that's the type of function, right? I'm just focused on the rate of change. What type of function has a constant additive rate of change? Constant additive. Linear, there we go, okay. Linear. What's the equation for a line again? Does this help remind anyone what the constant additive rate of change is? It's in that equation somewhere. M, but what does M stand for? Slope. Remember, slope is multiplied because what is multiplication? Repeated addition, right? So I know that's a very different, that's a jump, right? But M is for slope, right? That's what we're repeatedly adding. So slope is my constant additive rate of change. You good with that? Okay, Miles, do you remember what the constant multiplicative rate of change is? It's an exponential function, right? But what's the name of that rate of change? This one is a little bit closer to literally what it means. It's a constant something. Anybody remember another word to indicate things that we multiply by? What? Factors, right? Constant multiplicative rate of change is a constant factor, okay? So hopefully that's a recap. By the way, does anyone know where we could have found those terms? Slope, constant factor, really important. Notice how I intentionally put linear function and slope right next to each other. Exponential function, constant factor right next to each other. Slope-intercept form of a linear equation and x and y intercepts, and we can determine the slope and constant factor when given any mathematical representation. If you can't mark that off, that's okay. That's what today is a lot of practice of. And then what we are working towards is being able to create two variable equations, x and y, for linear and exponential functions, graphing linear functions, graphing exponential functions, and developing tables. So that's what today's practice is all about. Okay? but it's through understanding those types of functions. So hopefully we can mark a lot of that off today. And part of that started yesterday with 1 through 3. Remember, we had to identify the y-intercept and the rate of change to note those things. And we picked up yesterday, I think we were here. Is that when we left off? Does that sound right? So we may be in slightly different places with this practice. Who missed yesterday again? Taylor. Yeah, you got the practice though. That's it right there. So, really quick reminder, the reason why you're in small groups is so that you are actively collaborating and talking about those things. I don't care who you are, you can always benefit by talking through these things. If you aren't 100% sure, then you need to ask questions. If you feel like you really understand it, you need to be explaining it. Because if you're asking questions to understand, you're going to grow and learn. If you're explaining it, you're going to grow and learn. It takes a deep level of understanding to be able to explain it to somebody else. I think if you look at the level 4 on here, one of the things is I can explain these ideas to someone else. So to get to that level 4, you got to be able to explain it to somebody. And if your whole group is stuck, what do you get to do? Go ask somebody. You got 9 groups in here, 8 groups, 1, 2, 3, 4, 5, 6, 7, 8 groups in here. There's at least one group that's going to have an idea. Use each other's ideas and learn and grow. I don't care how you learn it, but I do care that you learn it. All right? So communicate with your group. Let's figure out where we're going to start based on where we ended yesterday. What questions do you have before we get started? Going once, going twice. All right, let's go figure out some details about these linear and exponential functions. Mr. Hobby and I will be around to help support you. So, first things first, learn your equations. We want to know those things. Learn the names of your rate of change. Guys, don't sit down. If you sit down, you're going to be less engaged. I need y'all standing in the center. I'll give you time to take notes in a second. Listen, when you are looking at these equations, do you know what, or looking at these functions,
There we go.
have you figured out what the very first thing you need to do is? What is it? If you want to write an equation, what's the first thing you need to do?
Slope?
Is it always a slope?
No.
No. The y-intercept might be important, but I need something before that.
Figure out if it's linear or exponential.
Yeah, if I want to write the equation of a function, I got to know if it's linear or exponential first, because they have different equations, don't they? Okay, so one, figure out, actually I'm just going to shorthand it, linear or exponential. You've got to identify that, because then, and this is going to help some of us that we're not doing, if it's linear, what could you immediately write down?
Y,
Yeah.
f of x is equal to n
And you can put y if you want. I like f of x because it's that function notation. But if it's linear, could that help you focus your attention on what you need to identify? Take advantage of this, right? And so now I know I want my slope. By the way, Landon, how do I calculate slope again?
I don't remember.
Oh, we just talked about it. So I was confident in asking you. Who else? Hope, how do we calculate slope? How do we calculate slope?
Is it the change of y over the change of x?
Change in y divided by change in x. And Kelly and Elizabeth, y'all looked at this earlier, right? When you looked at a graph, how did you try to do it? Rise, divide, by run. Remember, guys, you can do it both ways. If you're like, hey, this is a line, could you graph those points to figure out what the slope is? You've done rise, divide, by run since middle school, right? Could you graph it if you wanted to? Yeah, you remember how I told you you can convert among the representations to help you out? You don't have to stare at a table, so don't. If you're stuck on the table, make a graph. That's totally valid. I highly recommend it. But knowing this can be very helpful here. Again, B, by the way, is what?
Y-intercept.
Y-intercept. That's actually going to be one of the last things I find, because the rate of change is what defines it. And we got to remember, a constant additive rate of change is called a slope. And when I look at the equation tells me the same story, because what's happening between m and x? They're being, oh yeah, because multiplication is repeated addition, right? It's telling the same story from different perspectives. There's beauty in this, okay? We got to learn how to look at different perspectives. Now, then fill in the values that you need, right? Once you have it linear. But exponential is a little bit different. What's the exponential equation?
F of x is equal to a plus b squared,
Times b squared.
or times b squared.
Be careful and remember. We're going to talk about squared soon. That's not exponential though. Because the number of times that you're multiplying by your factor can change. What can represent change though? A variable. So I'm repeatedly multiplying by b x number of times. One of the most common mistakes that I see students make is this. I see this a lot. I see this a lot. I see this a lot. But remember, this literally means what? This means what? Addition, right? Are we adding with an exponential? No, what are we doing? Multiplying. We're not just squaring, because squaring indicates I'm multiplying by b how many times? 2 times. But I'm multiplying by b 2, 3, 4, 5, 6 times. I can even go backwards and divide by b 1, 2, 3, 4 times, right? So the exponent needs to be a variable. Okay? And the b is what I'm repeatedly multiplying by, is why it's got the exponent. A is the y-intercept. And so 2 things I want to point out about this is, I know a lot of students get tripped up when they look at that exponential curve. One of those common things is to go, hey, it's going up 4, and it's going to the right 1. But what idea is that to say it's going up 4 to the right 1?
Slope.
That's slope. But is slope the constant multiplicative rate of change?
No.
No. So keep that in mind. That's why you need to identify the type of function, because as soon as I know it's exponential, I know, oh, I should put this, that's not going here. I should know, hey, I'm not looking at slope, I'm looking at a constant factor, right? Once I know it is talking about exponential, it's a constant factor. And so this is what I recommend. If you haven't seen me do this yet, notice, and it's easier on this one, it was really hard on number 5. But if I start with 2, before I figure it out, do I know what I'm multiplying 2 by? No. So I do 2 times f. I don't know it. And if I take 2 and I multiply it by f, what do I get?
6.
Can I solve that equation? What would I do? Divide by 2, so 1 divided by 2. The reciprocal, the 1/2. 2 divided by 2 is 1, so what is f? And 2 times 3 is 6. 6 times 3 is 18. And if you were to go backwards, notice this was not a 1, it was a 2/3. Right? Because 2/3 times 3 is 2. So be careful with those. It was a little hard to see on the graph. That's why I'm bringing that up. What questions do you have about this little notation about linear and exponential so far? Okay. One last thing then before we continue. Oh, actually 2 last things. 1, do not ever forget for a y-intercept, what do we know about every y-intercept that has ever existed? What's 0?
The x-intercept.
The x, well, not x-intercept, the x, yeah, the x value or input. So be careful, right? Because if I say x-intercept, I'm only talking about the point on the x-axis, but the x value or the input is 0 for a y-intercept. And so you can create a graph, by the way. For those of us who are stuck on the table, could you have created a graph to find the y-intercept? Yeah, right. But if you find your input of 0, it's a little bit easier as well. Last thing that I want to note before I have you do some notes for your future forgetful self. This equation, super, 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 super duper close. But there's one small error and we need to learn from this. What's being repeatedly multiplied in C? What is it? 3. Why is it only the 3 that's being repeatedly multiplied? Because it's what? Notice the x is technically right now only on the 3. What do I need to do to fix this so that it's the entire 3 halves that I'm repeatedly multiplying? You see how that groups the 3 halves together? That's another one of the most common, very simple mistakes, and I know what you intend, but it's not quite the same thing. If you were to type what you originally had in here in the graph or in the calculator, it would not give you the same function as this. So remember, And this is partially due to that order of operations. What happens first, an exponent or division? An exponent happens, right? Parentheses, then exponents, then multiplication and division. Notice what's happening before division? So you would have done 3 to the x before you divided by 2, but I need the 3 divided by 2 first. So there it is. I need the parentheses to indicate that I'm dividing first. Okay? I want you to grab a seat, do notes to your future forgetful self on either the tables or on the graphs, whatever you need to. Maybe you just put it on this practice here. Could I make a graph and then figure out what type of function it is? Yeah, convert among the representations. But at the same time, when I look right here at number 9, that looks super funky, right? So can I make a graph of this table? 100%. But just looking at it, any guesses whether it be exponential or linear? Or neither? Linear maybe? Okay, so if it's linear, what's happening? Which type of constant? So we've got to break ourselves, right? You've got to remember, because there's constant additive and there's constant multiplicative, right? So we think constant additive. So if it's additive, what am I doing to 20 to get to 15? Remember, it could be adding or what? Subtracting. What would I subtract by? Okay, is 15 minus 5 45 divided by 4? Right away, Kelly's like, right? Guys, what is 15 minus 5? 10, so that's a good check, right? So is it linear?
No.
And so that's what I would check, right? I'll be honest, I would always check linear first because it's easy to add and subtract, right? Okay, so it's not linear. Boom, that's out. So what are we thinking possibly now? Maybe what? Maybe exponential? Maybe? We don't know, right? But it might be. But if it's exponential, right? We just checked additive. If it's exponential, what do we know about the rate of change? It is multiplicative. I'm not saying it is. I'm just going to check. Do I know what that multiplicative rate of change is yet?
Yes.
What is it?
3/4.
How'd you get that?
I did 15 divided by 20, and then it gave me 3/4, and then I took 15.
Why'd you do 15 divided by 20? Where did that come from?
The two numbers on the table.
But why'd you divide them? Can anyone explain to me why she divided?
Because if I multiplied them, it would have got me a bigger number than I needed.
Okay. There's something else here. I've talked about this multiple times in multiple groups. Before Crystalline figured it out, does she know what the constant factor is? No, Mr. King. Guys, do we know what the factor is right now? Ignore what Crystalline said. Do we know what it is? No, so what can I use to represent something I don't know? A what? Variable, and it's a constant factor, so what's a good variable to use?
Yeah.
So if it's exponential, aren't I multiplying by f all the way through? And so I could say 80 divided by 3 times f is equal to 20. Or 20 times f is equal to what? 15. Hey, by the way, what would I do to solve this equation right here? I would what? I would divide by,
1/20.
so I'd multiply by 1/20th, right? Divide by 20. And what's 20 divided by 20? Hey, what's 15 divided by 20? Is that what Crystalline brought up earlier? I'm trying to help you take the guesswork out of it, right? I want us to notice, right? If we say it's exponential, we're constantly what? Multiplying. I'm not trying to make it tricky. Use that idea of constant multiplication. It's harder to see sometimes, so multiply by f. And so f is equal to, if I check it right here, if I let f be 3/4, hey, what's 3 divided by 3? 1. What's 80 divided by 4? Oh. So is that constant factor 3/4? Right? And so we need to recognize that. That constant factor is 3/4. That's how I would find it. If I multiply everything on the way down, notice this. Hey, what's 15 times 3? Divided by 4. Right? So what equation should I be using for this function? We said it's what type of function, by the way? Exponential, so what equation do I need to use?
A times
A
B.
times B squared.
Is it only multiplied by b 2 times?
No,
No, it needs to be in x. I'm starting at a and I'm repeatedly multiplying by b. I don't know how many times. All right, so which of these values do we already know? Substitute values in.
B.
We know b. We know what we're multiplying by. What are we multiplying by?
3, 4.
Now, do I have a? What do I mean by a here? Kyron, what do I mean by a?
You have it all.
Okay, so let's hold on to this. We need to know this. Bella, what do we mean by a here? Looking for your notes on it? You're good. Let me pause and remind you, I have the rate of change. What's the other piece of the equation that I still need? The y-intercept, right? So slow down. Don't just try to memorize. Think through and make sense of this. I have my rate of change. What do I still need? I need the y-intercept. I need to know where I'm starting. What do we know about every y-intercept that has ever existed? The what? It starts at 0. Well, the input is 0. Do I have that yet? No. Right? So I can find it though. I'm multiplying by 3/4 to go this way. So to go backwards to that 0, what do I need to do? Divide by 3/4. Man, I can type that into the calculator, by the way, but that kind of looks ugly. Do you know how we mathematically divide by a fraction, though? Do we remember? Multiply by its reciprocal. Remember how I asked y'all to practice with that reciprocal early on? Because it's easier to do this. What's 80 times 4? 320, right? 8 times 4 is 32. And I got times an extra 10 in there, so 320. And what's 3 times 3? None. I need my rate of change, and I need my y-intercept. We got to recognize that if I'm going times 3/4 this way, to go backwards, I'm going to divide by 3/4. But it's way easier to just multiply by its reciprocal. But also you got calculators. Davis, it looks like you got a question. Okay, there's a group up here if you want to move up here. Take what notes you need to. After you finish those notes, Mr. Hobby passed out a sheet of paper with 6 graphs on it. It's got 6 equations, and I want you to create a table and a graph for each of these. We're going to run out of time before Demonstrate Understanding today, so we're going to start tomorrow with the Demonstrate Understanding. It's going to cover everything from that practice, and it's going to cover everything from these sets of graphs. Be aware you also have some practice with Check Your Understanding. I will also work on creating a solution set with Mr. Hobby during second block planning. And so if you want to come back and get a solution set to this practice, you can come back and get that. Okay? But let's go ahead and start working on that numbers 1 through 6 with you guys. You know what I'm seeing around the room? Really quickly, I do want to point this out. At the end of the practice that we skipped, there is this verbal representation section, and it's hard to write equations from verbal representation sometimes, but what could you create with numbers 12, 13, and 14 to help you write these equations? What could you create to help you? You can make a graph. What else could you make? A table, right? Don't forget that. But what I want to talk about really quickly is here. I want to point this out. A lot of us are super comfy with linear, right? We've been doing linear a long time. When I look at 3/2 x minus 7, what feature of that function should immediately jump out? The -7, what is that? Y-intercept, right? So -7. What's that 3/2 then? Slope, that's my rise divided by my run. So I'm going to go up 1, 2, 3 to the right 2, up 1, 2, 3 to the right 2, up 1, 2, 3 to the right 2. And I got a nice little line here. And so one thing I want to point out, because it's going to help you a lot with exponential, most of us, when we did a table, didn't we just grab the points from that graph? Can we just grab points from the graph?
Yeah.
Is that okay? 100%. However, I do want to remind you of this. Don't forget to check with your equation. Right now I just made 2 the what? The x, or what's another word for that? That's my input, isn't it? So I've substituted in for x. 3 minus 7 is what?
-4.
So an input is 2, has an output of -4. Is that what we see right here on the graph? So if I wanted to go backwards and maybe get f of -4, right? I could do 3/2 times -4 minus 7. The -6 minus 7, which is -13. So this is something super valid to think about. You can always substitute inputs in and get outputs out. The last thing I do want to point out with number 1 is this. I know that my y-intercept is typically my starting point, but if I'm making a table, it's actually usually in the middle for me. And I'm going to go a couple points to the right and a couple points to the left, and I can use my rate of change for this. What am I doing to the y values? Adding 3, what's happening to my x values?
Plus 2.
That's why I went 2 and 4. Same exact story. And I can go backwards in the same way. And so I'm going to connect 2 important ideas. I want everyone to notice. Oh, I got erased. Just kidding. Oh, maybe I'll just have it on your sheet of paper. So one of the things I saw a couple of groups noting, and I think this group over here noted it, and I know the 10s noted this. If you're looking at g of x equals 4 times 3/2 to the x, what is that 4 right there? That's my y-intercept, right? An input of 0 gives me an output of 4. And what's happening to that exponential function every single time? It's being what? Multiplied by what? 3/2. Now with an exponential, it is pretty much always going to go by 1s. You can keep it going, or you can also go backwards, which you'd have to divide by 3/2 to do this. Okay? But at the same time, right, I'm using my rate of change to fill out that table, but can't I also just substitute -1 in? And you know what I get when I do 4 times 3/2 to the -1 in the calculator? Which I would just use a calculator, by the way. Same thing here, probably just would have put that into a calculator. Can someone do 4 times 3/2 to the -1 for me? Four times 3/2 to the -1. 4 times
6.
3/2 raised to the -1.
Oh,
103.
yeah. Wait, you did it wrong.
Be 8/3.
Wait,
8/3. Did you put parentheses around your 3/2? Make sure you put parentheses, but it should be 8/3. Just like I wrote right here.
wait.
Okay? So listen guys, if you're making a table, there's 2 ways to make a table. Substitute inputs in to get what? Outputs out. Or identify your y-intercept and use your what? What do we use to get the rest of the points? Rate of change. Okay? In tomorrow's demonstrated understanding, I'm going to go ahead and tell you there's going to be one exponential and one linear at the end. I'm going to ask you to take the equation and give me a graph and give me a table. Mr. Javi and I will work on a solution set for these practice, but there's also the check your understanding. The check your understanding problems have all of this in there along with answers already given. So please study your linear, study your exponential. Shoot me an email if you have a question. By the way, is there anyone who is up for doing the Hero Friday?